Welcome to our evening presentation. I'm James Parsons, Chair of the Wales Group, and I'm sitting in tonight for Keith Williams, who's unable to chair this evening. Alan Hayward is well known to many of you. His whole career has been in the design and construction of bridges. With over half a century of experience, he's designed and been involved with the construction of more than 200 bridges, and of those, 8 have won national awards. He started his career training with British Railways as an articled apprentice from 1957, worked for various contractors and a consultant, including overseas. And when he returned to the UK, he was appointed Chief Engineer of Fairford Mabey here in Chepstow. In 1983, he co-founded Cass Hayward and Partners, consulting engineers specialising in all sorts of bridges. Although now he's retired, he's still a consultant with the firm. And when he's not working, still enjoys his hobbies, which include cycling, painting, and actually not just wine, but running a U3A wine appreciation group. So, Alan, I hand over to you. Thank you.
Thank you, James. Well, good evening, everybody. I'm flattered so many of you turned up to this talk, which I gave probably 2 years ago in the Civils, and I think I've given it to the history group of the Structurals in London probably 6 years ago now. I've updated the talk a little bit because things do move on, obviously. Things like high-speed rail is here, HS2, etc. So I'm going to cover a bit more, I think, on the recent introduction of train loading and what's going on. But you'll see on the slide there, you've got an old slate bridge on the left, 19th century thing. As far as I know, that bridge may still be there. I'm not sure. It was just for a 2-foot gauge slate mining railway. And on the right, you've got a viaduct in France, the Viaduct de Vicoin, if I can get my French right, on the TGV system. And that's been an inspiration, I think, for some of the bridges that are going to go in on HS2, which I'll come to later. Now, this talk is going to be my views. I do pop in the occasional opinion, which is just what I think, and it's not necessarily what anyone else thinks, or Cass Hayward, or anybody. But anyway, we'll proceed on. So what I'm going to do there is talk on 4 little headings. Number 1 is the trains. I'll talk about the development of trains since 1825 to the present. Then a bit about the bridges, developments of those over the years. And the one on the top right is one of it's now a Network Rail standard box girder, which came out of the so-called Western Region standard boxes of the late 60s, but actually were originated in the Midland region of British Railways in 1960. And then I'll talk about bridge loading, bottom left, the ancient loading assumptions that were used, and then coming right up to date with the current loading that's used by Network Rail and obviously on things like HS2. And then finally, a little bit about bridge failures, because I think we can learn something about things that have gone wrong in the sphere of loading. So the trains now, we're going really back to 1825 here. The Stockton and Darlington Railway locomotion was built by Robert Stephenson and Co., a famous company who built steam locomotives in Newcastle. Robert Stephenson was the son of George Stephenson, of course. We can see the tiny engines in those days, and the second one down is the famous Rocket, of course, on the Liverpool and Manchester Railway of 1829. That got up to a speed of 29 miles per hour, which was phenomenal at the time, and took part in the famous Rainhill Trials competition. And one at the bottom, the Globe, funny little engine that, again built by Robert Stephenson to a Hackworth design, who was another famous locomotive man. That engine apparently reached a speed of 50 miles per hour, which I find that difficult to believe, but that's what I've read. Built in 1830, but the boiler exploded in 1839, so perhaps it wasn't that successful. But bottom right is moving towards what we might begin to recognise as a sort of proper steam locomotive, getting longer and the weight is going up. There's a development throughout the history of the weights of locomotives increasing steadily, from the tiny 4 tons of the rocket right up to well over 100 tons today. Now, Mr. Brunel, he comes into everything, and he was famous on the Great Western Railway, of course, from London to Bristol. But he was, of course, the civil engineer. He ordered the locomotives, and he made the statement there that no locomotive is to weigh more than 10.5 tons. And if it's above 8 tons, it must have 6 wheels at least. So that's what Brunel said. But what happened, the first locomotives were a lot heavier. And this is a recurrent theme, in fact. Things get heavier as you go on without unintentionally. So this famous loco, the North Star, again built by Robert Stephenson, you can see here weighs 18.5 tons, so the weights are going up, and the axle load is 8 tons, so that's going up as well. 8-ton axle is tiny, of course, present day, but it was very big at the time. I've done a bit of a survey of locomotives over the years. I'm not going to go through all these figures, obviously, but this is the sort of middle part of the 19th century. The interesting ones to look at are the axle load steadily going up to 18 tons by 1868. And the weight of the locomotives are also going up to approaching 50 tons. So it's a steady increase the whole time. But all these engines were built by all the different railways, of which there were dozens and dozens, of course, all doing their own thing, really. It wasn't really a joined up railway. Now, this monster was on the Bristol and Exeter line, and a huge driving wheel. You can see 9-foot diameter. There's nothing ever bigger than that. Peculiar engine. It had a fixed wheelbase, and the driving wheel, the big one there, had no flanges on it. It was a flangeless driving wheel. Now, this had a heavy axle load, 18.5 tons at the time, and there was a high-speed derailment near Bristol of that locomotive. And a lot of these early derailments are really the cause is heavy axle loading, because the track wasn't really up to it. So if we move on now towards the end of the 19th century, the weights are going up of the locomotives. We're up around 50, 60 tons now, but still around an 18, 19 ton axle load. So that's going up more steadily now. And this famous locomotive, the Stirling Single, which was the Great Northern Railway from London King's Cross to York, really. Again, big driving wheel, and at least 2 of these derailed at high speed between in 1895 and 96. Again, it's the high axle load on doubtful track. This is a recurrent theme. Just looking at that engine, you can imagine the hammer blow you might get off that. All the hammer blow is on this single axle. So high hammer blow may well have contributed to the derailment. We don't know. So we move on through the early years of the 20th century now, and the loads are still going up. We're up to a 21-ton axle and a nearly 90-ton weight of locomotive. And then we get really to the zenith, what I call the zenith of steam in the 1920s and 30s. And these are more things some of you may recognize. And 22-ton axle now, and locomotives built in the 20s and 30s. The real zenith of railway traction, really, between the World War I and World War II. And this moves on towards the present day, and weights going up, but only slightly now. We never exceed an axle load of about 22.5 tons, but the weights are up at 105 tons, the weight of the Duchess locomotive there, the fourth one up from the bottom. So that's the sort of development. And it's sort of summarized there. And at the bottom, sorry, if we move back, the bottom there, you see the 100-ton bogie wagons. These really came in the 1960s for coal traffic and oil traffic, weighing all up 100 tonnes. I'm speaking old British tonnes here, not metric tonnes. Would be 102 tonnes metric tonnes, but 100 tonnes old tonnes. And obviously with a 25-ton axle load, higher than we've ever had before. And the loading of these has really overtaken from the locomotives. Up to that time, up to the 1960s, it's the locomotives that governed everything, the loading. And the carriages and the wagons were really very much lighter. But the wagons really took over the situation from the 1960s with these bogie coal wagons and oil traffic, and also ballast trains as well for terminal way work. And what happened with diesel and electric locomotives from World War II, really. And these have never exceeded an axle load of around 22.5 tonnes. But the critical one these days is the one at the very bottom. The Class 67 is more critical for what we call route availability because it only has 2 axles to each bogie. So 4 axles altogether, whereas most of these diesels have at least 6 axles. And going back a few years, you see one there that's got 8 axles, called a 1 Coco 1, and the little wheel at the front was really to reduce the axle loading on a very heavy locomotive. So the Class 67 is the rogue, really, built for parcels trains. But of course, parcels traffic has disappeared off the railway to a great extent, but these engines are still used. In fact, one of them is the Royal engine for the Royal train. This just summarises the development of the weight of locomotives. You can see the steady, almost constant increase from less than 10 tonnes up to over 100 tonnes. And the big red blob there is the 100-ton bogie wagon I mentioned. And at the bottom, you can see the progress in axle loads. Again, a steady increase over the years, but flattening off. But these 100-ton bogie wagons dominate now for the loading. Of course, this sort of thing, right up until the 1960s, was most of the goods traffic. These 10-ton coal wagons were everywhere. Only weighing 16 tonnes roughly altogether, an 8-ton axle. So as far as bridge loading, really negligible loading. But of course, these 100-ton coal wagons came along. Now, I took that picture probably 9 years ago now. And of course, the coal traffic is now, at the moment anyway, has disappeared. There is some imported coal, but hardly any mined in the UK. So that traffic's disappeared, which I suppose might be a relief to those maintaining bridges and track. But the modern trains we have now, of course, we had the HST, the 125, came in the 1970s, only a 17-ton axle. That really helps for route availability, as we call it, RA5. RA10 is the top route availability for the heaviest rolling stock, i.e. the 25-ton axles, 100-ton wagons. And this, the later Hitachi Class 800s, they're running west out of Paddington and north out of King's Cross to Edinburgh, are only RA4, so very good rate of route availability. On the other hand, they're going a lot faster, so the impact effects are larger. So moving on to the bridges now. This just tries to summarise some of the developments over the years. In the early years, we had cast iron, was used extensively for beam bridges, and or masonry arches, or timber. And there were hundreds, if not thousands, of timber bridges all over the system, including many famous ones by Brunel in the West Country. And there are still 9 of those in mid-Wales, actually. But masonry arches, of course, have stood the test of time. Cast iron, of course, was taken out, which I shall come to. And then you've got at the bottom left what came in, wrought iron and steel, with a very popular method was what's called a troughs, where you have the rails set into longitudinal timbers instead of sleepers, sitting into troughs. And that was a very economic method of construction. giving you the minimum construction depth. The depth from the rail level to the underside is very shallow, so that meant you could get good headroom over rivers and small tracks and so on. So a very popular method of construction. And then we had what's called the half-through bridge at the bottom there, generally riveted, always riveted in the 19th century, and again gave you minimum construction depth from rail level to the underside. So that was extremely popular. But then moving on from the 1940s, precast concrete came in. Actually started a lot earlier, just after First World War, but came in extensively from the 1940s for small spans for economic reasons. Obviously, no maintenance painting to have to do. And then we had this thing called the Western Region box, which has become a Network Rail standard, which more of later. And then we had a very popular one, the Standard Type A. That's the third one down from the right-hand side. The Standard Type A bridge, a very popular design from 1960. And there are probably hundreds, if not thousands, of those still around on the rail system. Again, the advantage of the shallow construction depth. And of course, the girders didn't extend above rail level. So that was good for general clearances. And then we had composite bridges from 1963. Very popular now, of course, for highway bridges for many years. But the railways, they didn't use composite of this type until early 60s. But obviously the thing there is you need construction depth to fit the girders under the rails. And then we've got the thing called the U-deck, which I'm ashamed to say we invented, which is very useful for small spans up to about 25 meters. And again, with shallow construction depth, a very shallow floor. So that's a little bit about the development of these small span bridges over the years. I won't deal with the big span bridges. They're obviously an animal to a totally different form. But an early long span bridge, of course, was this one, Rivertees Bridge at Stockton, a suspension bridge, a big mistake for railway traffic, designed by Captain Samuel Brown. He wasn't really a bridge engineer at all, but he built this bridge anyway. But the deflected shape I've shown there is a bit of an exaggeration, but this bridge deflected in a frightening manner, and they had to take it down after a few years. It only lasted about 15 years. So it's an example of what not to do, and apparently the drivers would see this sort of bow wave in front of them as they took the train across. It must have been quite frightening. And masonry arches, I mentioned, really have a very good for durability, especially the masonry ones, brick as well. The disadvantage being the headroom, of course. It's very restricted. Now, I mentioned timber viaducts. There are 9 of these in mid-Wales. This is one of them. And these were built in the 1860s and very cheap. I mean, the reason they went for timber is it was so cheap. And the cost of these, I gather, was between 30% and 50% of the cost of a wrought iron bridge. And very lightweight, of course, timber piles, and took advantage of bad ground conditions, really. 9 of them have survived. There are many more been taken down and replaced. And over the years, the maintenance is quite a problem, of course, and various timbers have to be replaced. And these days, Network Rail are replacing using hardwood, green heart timber, which has a very long life, whereas the originals were built in pine, which obviously has a comparatively short life, perhaps 20, 25 years. Just a typical underview of a typical wrought iron or steel bridge of perhaps the 1870s to 1900. Typical construction, main girders at the side, which it's just a half-through type of bridge, cross girders and rail bearers directly underneath the rails. And you would sometimes have ballasted track on the top of that, or sometimes longitudinal timbers. But you can see I've just highlighted there, the rail bearers are of course critical for wheel load. They're designed entirely up for a single wheel generally. Cross girders are critical for axle loading, single axle, whereas the main girders are critical for a whole train. I mean, that's pretty obvious. And the bearings, of course, are decided on the train load. Notice the bridge is very skewed. There are lots of skewed bridges, and skewed bridges over the years tend to give problems. And things tend to twist, and you get funny things going on at the bearings here. But a typical method type construction, and there are hundreds of these still around. Riveted construction, of course, not welded. But cast iron has survived in places, although cast iron was banned for new construction in around 1870, and for new construction, and banned totally in 1891. Some cast iron beams do survive as edge girders, where they don't carry rail traffic, but here you can just see carrying a parapet. And I mentioned cast iron was banned totally from 1891. Well, it didn't happen very quickly. It took about 70 years. This is a bridge I was involved. I did design that in 1962, replacing cast iron with precast concrete units. So this was West Coast Main Line. I mean, staggering that this cast iron did survive until that time. And I mentioned the typical standard type A bridge from 1960. There are many of these on the all over the rail system. And they were often put in to replace this trough construction with longitudinal timbers that I mentioned, which is pretty dreadful for maintenance. I mean, the timber tends to rot inside the trough. You can't see what's happening. Moisture collects in there, and the trough sides, of course, are not accessible, so you get corrosion, and the whole thing is bad news. And adjusting the permanent way is also a problem. And there have been quite a few derailments to this day. There was one in the last year on longitudinal timbers. This sort of thing has gone on over the years to strengthen bridges. This shows what's called top hat strengthening. There's an old bellied girder originally, and then this additional top hat has been placed to strengthen it. Not ideal, of course, the girder in the what's called the 6 foot space between the rails, especially where you've got the southern region. You have the conductor rail as well. Not an ideal thing for maintenance or accessibility, but sometimes it's what you have to do. And the first pre-stressed concrete railway bridge in the UK, 1947, a long time ago, made by British Rail in their works, Manchester, Newton Heath. And that works was quite a something. They used to make steel beams there, steel bridges, concrete bridges, precast work, including this quite revolutionary design. And that bridge is still there, and I think it's probably doing quite well. And I mentioned composite construction with the girders underneath, and here you see one of the first of those, 1963. I was resident engineer on that bridge. And the novel method there of erecting the precast units with a forklift truck. That's been done since, of course. Notice the shear connectors. We would use shear studs these days, but in those days we used these bits of channel section welded on the top. A bit more expensive, but it did the job. This was replacing an 1850s box girder, a Robert Stevenson style of wrought iron box girders there, which were in bad condition. And I mentioned the U-deck, which has come in from 1997. The very first one we did was at Dunton Green, south of London, and that had an all-steel floor, whereas in later editions we've used a composite floor. Advantage here is the underside of the bridge is totally flush, so it's good for maintenance, avoiding traps for pigeons to build their nests, and quite a nice looking bridge, we think. And that's become now a standard network rail design, adapted from our starting point, I suppose. Some of the details they've got on the standard I wouldn't do, I have to say, but there it is. We tend to use our own details. And the modern sort of half-through type bridge, you would call a D type, I guess, with a single track between two girders. And that, in fact, replaced River Ex Bridge at Exeter, replaced a lattice girder bridge where there were some brittle fracture failures in some of the members there. So that bridge had to be replaced. Now this is a very recent bridge, in fact on the North Yorkshire Moors Heritage Railway, recently constructed, of what we call the generic E-type, which is an adaptation of the E-type really developed in the early 1960s. We've got our own version of this. I tend to use this detail for the end trimmer. I call this a sit-on trimmer. You can see that the short cross girders just rest on it, so the connections are very easy. And the trimmer goes underneath the main girder, with the bearing is underneath the trimmer. And that really simplifies the construction. The little shot bottom left, there's a diagram from the Network Rail standard, where the trimmer they use on skew bridges has 3 bearings, that's the limit deflection, and the main girders have their own bearings. So you've got no less than 5 bearings at the end of the bridge. Well, why have 5 bearings when 2 will do? Trouble with 5 bearings, do they all fit and carry the load you want them to? I somewhat doubt that. So this is a detail I've used on a few bridges now, and it seems to work. And this is an example of another one, Gainsborough, in the 1990s, and that has in fact got sit-on trimmers underneath the main span, the main 2 spans there, and underneath these approach spans at each end as well. And that replaced a very early box girder bridge of 1849 by, I want to remember his name, which I've forgotten, famous designer, Fourth Bridge, Fowler, John Fowler, yes. Wrought iron box girders continuous over the intermediate support, but in the late 80s, early 90s, they discovered some fatigue cracking over the top flange there, so the bridge became life expired, so it was replaced by this generic E-type, I would call it. Moving more to the present then, high speed has come along. High speed means faster than 125 miles per hour, and some bridges on the East Coast main line have been designed for higher speeds, and of course HS1 was designed for higher speeds of 186 miles per hour, and of course HS2, which is now under construction, will be even faster than 186. So the first bridge to be completed for new criteria which have been brought in for high-speed traffic, because you get increased vibration and problems on the high speed, creating accelerations as a train goes over its speed. And this effect of vibrations has been known. In France, they found it dislodged the ballast or made some of the ballast unstable, like quicksand, if you like, which is quite dangerous, of course. So to cut that out, they've introduced new criteria for high-speed trains, and that generally means stiffer members. So the members under the floor of the bridge are stiffer to cut down that effect. And also the other effect is comfort of passengers. When you're travelling on a high-speed train across the bridge, you don't want your cup of coffee in your lap. So to increase the comfort, there are criteria of about 0.1 G for passenger comfort. So these criteria have come in, which I shall cover shortly anyway. But so you'll see there the HS2, this is one of the projected viaducts, which has got its inspiration from France largely. Jolly good design, I think, which would be launched. And I think the French are going to build this, which I find a bit disappointing. And I hope on the next batch of bridges that the British contractors can get in. So on to bridge loading now. What do we do about, we know the weights of the locomotives, we know something about the bridges, how are we going to design them? So bridge loading, I've just put this on to show that when you've got 2 steam locomotives, you've got some pretty hefty loading on a long span, of course. These locomotives look pretty identical, don't they? But they're different. The one on the front is called a Hall 2-cylinder, and that gives you a lot of hammer blow because you've got unbalanced motion. and the hammer blow is in fact 19 tons on those driving wheels, whereas the latter engine, the King class, has 4 cylinders, got 2 on the inside, 2 on the outside, and that gives you a balanced system. Everything balances out, so you don't need so much balance weights on the driving wheels. And so the hammer blow is only 3.6 tons compared with 19. Makes a tremendous difference to the suitability and capacity on bridges. I just put this on to show, I think I mentioned this before, axle loads govern short spans, locomotive or engine loads govern medium spans, perhaps a 30 foot. I'm sorry if I keep using feet and inches, it's a bit old fashioned, I can use meters. Train loads, of course, governs the longer spans where a whole train occupies the span. So what did people do in the early days? Well, there was a statement here made at the opening of the Royal Albert Bridge, that's Brunel's famous bridge across the Tamar. Colonel Yolland said that the normal train loading was equivalent to 1 ton per foot run, and that was what people were doing at the time, 1830s, 40s and 50s. And all they were doing, they were getting the weight of a locomotive, say 25 tons, dividing it by the length, which if it was 25 feet, 25 over 25 equals 1. So that was the design loading. They did nothing about the concentration of axle loads, nothing about impact. That was it. You just spread the weight of a locomotive uniformly. Pretty crude. Very surprising if you think about it. The design of bridges was actually very advanced. I mean, if you just look at that structure, it's marvellous. And so everyone knew about structural engineering, how to design trusses, plate girders and everything. But when it came to how to estimate the effects of a train, it seemed to be totally missing. I think it was because these guys were coming in from building canals and things like that. They weren't really used to high-speed trains. So we had a collapse, 1847, the famous D Bridge collapse. And this was, again, the famous Robert Stephenson. He designed it. And it was quite a big span, 105 feet, I think they are, made up of 3 cast iron girders joined together because you could only cast practicalities of cast iron in short lengths. So they joined 3 together and then sort of trussed it up with wrought iron bars as a sort of pre-stressing system. But the system was fundamentally flawed. It didn't work. There were quite a few bridges like this, but they were soon condemned. And one of these failed, this bridge here. The locomotive got across the gap, but the carriages didn't. 5 killed, 20 injured. I mean, as soon as you get deaths on a bridge, you get an immediate outcry, of course, naturally. So there was a big inquiry about it all, and the experts were called into the inquiry. What do you do about train loading? And Stevenson and Locke said 1 ton a foot. Brunel, Fairbairn and Fox had a bit more, 1.5. And Hawkshaw, who was always a bit conservative, said 1.75. But people were doing their own thing, and that was all they were doing. It was just the weight divided by the length, and no allowance for impact or anything. Very surprising. And Joseph Locke, another famous engineer, a lot of railways in the northwest of England, he said he had heard that the Midland Railway were ordering engines of 32 tons with a wheelbase of 16, which means kind of 2 tons per foot. And he said, I think it cannot be. I would not consent to it running on any railway of mine. And that's what he said. But remember, at that time, we did not have a joined up railway. It was all people doing their own thing. And so Locke would only run his engines on his railway. It didn't join up to other railways to any extent. We didn't have a joined up railway system until much later. And there was a report produced, 1849, where they said the factor of safety, they expected of a factor of safety of 6 against failure, which sounds quite generous, and I guess it was at the time. But that was a sort of compensation for the fact that they weren't allowing anything for impact, that they just use a very high factor of safety. And they also said in the commissioners said these rules equally apply to the main and the transverse girders, and the latter, the transverse girders, should be calculated for the heaviest weights carried by the driving wheels. So at last, somebody was worrying about axle loads, which is quite something, of course. So that was an improvement. And they also said something about impact. The dynamical increase in bridges of less than 40 feet is of sufficient importance to demand attention and may even, for lengths of 20 feet, become more than 1/2. So that's suggesting an impact factor of 1.5, which of course is quite an advance. Unfortunately, not many people took notice of that. People carried on in their own way. And we move on to late 19th century, and an organisation called the Railway Engineers Association, which was all the railways sort of pooling their knowledge. And they produced this curve based on all these different locomotives of different sizes, weights, produced this curve of span against uniform loading, or equivalent uniformly distributed load, we call it, or EUDL. So this is the sort of UDL equivalent of the different disposition of the axle loads. So that was produced, and with the idea that all the railway companies who were beginning at last to get together to do the same thing. But the interesting thing, the statement at the end, it is worth reading. It is, I presume, intended that the members of the association should use their own discretion in regard to permissible stresses to allow for impact and deterioration. So they were leaving it to the railways to decide, individual railways to decide what to do about impact. So it just shows that perhaps the ignorance that was around at the time. And I've got here just a graph for interest showing the different assumptions for what we call EUDL, the equivalent uniform distributed loads, against span. And you can see right at the bottom then Stevenson and Locke on their 1 ton a foot. And then we move on through these various people, Stoney and Baker, that's the famous Baker of the Forth Bridge, producing their own curves for this. And then this one I've just shown on the Engineers Association of 1909, which is this green line. And then above that, what's called the 20 units of RA1, which I shall come to, which is the standard loading we use for route availability system now on the railway generally, including Network Rail. That's the current loading for assessment of existing bridges. And above that, even still, is the present day loading that came in after steam trains disappeared. In 1973, it came along what's called UIC 71, or RU came into in BS 5400. And that is another big increase. And you can see the enormous increases. And this is just static load. This has nothing to do with dynamics. It's just a static load span against EUDL. But some formulae were around due to various sources. Pencoid, an American formula. This was an impact formula, an increment. In other words, you add this little figure I to the static loading to get an increment. So you add 1 to this I. So 1 plus I is the impact factor. And then they did some tests, the Ministry of Transport did some tests in 1921. They came up with that little formula. And then in the first edition of BS 153 in 1923, a very similar formula, slightly updated, produced in 1923. So as late as 1923, this is all we had about impact. Pretty crude. But if I hark back to the commissioners, back to the 1849, if you look in their Appendix B, which had 83 pages, it takes a lot of reading actually, but hidden in that document of 83 pages, in 1849, is this little formula and this little table. And that gives you really everything you need to know. It's the impact. It brings span squared into it. It begins V squared, which is speed, and deflection is the deflection under the static load. I mean, that's taking into account all the imponderables, really. And I've tried it. At the time, of course, it was only applicable to short spans and to very low speeds. But I've tried extrapolating it to, by curve fitting. I came out with a little formula, and it's actually pretty good. It's a mystery to me that 1849 that was produced, but nobody seemed to use it. Probably because it was hidden in between 83 pages of small writing. There were some tests done in 1921. Everyone was beginning to get alive to impact now, and they did a lot of tests of different locomotives on different places on bridges and all these different test results. And they produced a curve MOT in 1921, which is the one I just showed you, a little formula. So things were progressing a bit in the 1920s. And in 1923, the first what we call RA1 loading. This again is just static loading. And this very much looks like two freight engines pulling a train of trucks, which is what it was. And that loading was developed to represent typical loading at the time on which you could base bridge design. And that loading, funnily enough, is still used today. It's still used by Network Rail to assess their current bridges on a basis of an equivalent uniformly distributed load to this loading. It's just a load system which you convert to an EUDL. And if you take 20 units of it, that's equivalent to RA10, which is the highest classification used for assessing bridges, and that's equivalent to a 25-ton axle load. Going down to number of units, 10 units of this standard loading is equivalent to RA0. You just take 10 off. So 20 minus 10 is equal to 10, and 10 minus 10 is equal to 0. That gives you the RA route availability. And there's the equivalent axle load to that. So you can see you go from 25 tons. So it means that most of the current locomotives around, which have a maximum axle load of around 22.5 tons, are around RA8, sometimes lower. That's a typical classification of modern locomotives. And the multiple unit trains, of course, are a lot less. They're more like a 16 or 17 ton axle load. So you're around RA5, RA4. So that whole system is still used today, although it goes back to 1923. There has been talk about updating it, but it's never happened. So we come to the question of hammer blow. At last, there was a major breakthrough. And after the First World War, there was a committee got together of the four mainline railways from 1923 to write a report and do some extensive research into the whole question of impact effects on bridges. And the main effect, of course, it was steam locomotives at the time, was the effect of so-called hammer blow from steam locomotives. And this is due to the part of the balance weights which are put on the wheels to counteract the reciprocating masses moving backwards and forwards. And this produces this alternating kind of loading on the rails. And the bit above the static loading is called the hammer blow. Hammer blow is a bit of a misnomer. You imagine a guy banging with a hammer, but it's not actually, or shouldn't be, the wheels lifting off the rails. It's just a local increase due to the effect of the spinning wheel and the counterbalance effect of the balance weights. And you can write formulae for these things, and there are various formulae around, but that's one of them. And it depends whether you've got outside cylinders on the engine or inside cylinders. It makes a difference. But they tested 52 bridges all over the railway system under many different locomotives, which had all sorts of different hammer blow characteristics, and came up with some results. And I've got this volume I keep in my bookcase, and it's a very valuable document. Interesting, they showed the variety. I mean, this locomotive here, the top one you see on the left, a Great Central C4, had enormous hammer blow of 13.5 tons, which meant that the dynamic axle load was about 32 tons, quite big. Whereas this much bigger engine here with 4 cylinders against the 2 had a hammer blow of only 3.6 tons on that driving wheel. So the maximum axle load was only 23 compared with 32. Terrific difference. So it just shows the enormous difference there was between all the locomotives. So after this report had produced, a lot of old engines like this were either modified or scrapped and replaced by these. So that was quite a thing that happened after 1928. And I just showed the bridge there. It's the Newark Dyke Bridge on the East Coast Main Line, which has been replaced in later years. So one I showed earlier, we'll show in a minute, for design for high speed. I can show here's a record you see of the deflection recorded under a locomotive having quite a lot of hammer blow on it. You can see the variation in deflection there, compared with a locomotive with hardly any hammer blow, going at the same speed, 36 miles per hour. So a terrific difference between the effect. Now in this 1928 report, their main concern was this hammer blow business. They didn't do so much about track defects, other than just at rail joints. They didn't do much about the effect of rough track, which I'll come to later. There's a famous example here on the Highland Railway in Scotland. These locomotives were built in World War I for carrying increase of heavy traffic going from Inverness to feed the Royal Navy at Scapa Flow, and they ordered these much bigger locomotives built by the North British Company in Newcastle to a design by one Fred Smith. And he produced these locomotives, or had them produced, with a static axle load of just under 18 tons. And the civil engineer said, well, you didn't tell me that. And Smith was called before the board of the railway and sacked. He said, you've ordered something that can't possibly be any good on our bridges and our track, so you're fired. So they sold these engines to another railway, the Caledonian Railway in Scotland. But in fact, Smith was reprieved because later, after the 1928 report had come out, and they worked out the hammer blow was actually much less on this particular locomotive called the River Class. And the total effect on the track was that the combined axle load was 21.95 against 21.35, only marginally more than the previous locomotives. So these came back onto the Highland Railway. So it's a bit of a funny story. And Fred Smith, in fact, was resigned. He had to leave the railway system altogether. Sad story. Now, there are other effects, of course, that not only vertical loading on railway bridges, you get other effects. One effect, particularly from steam locomotives, is lurching, which is really a rocking movement from one rail to the other that you tend to get. And particularly 25% of the load on one wheel can be transferred to the other wheel. So that's a matter for design. The Eurocode has got a similar thing, only it's not really, it comes to the same thing, but it's called eccentricity of vertical load. It's saying that the track might be in a slightly different position. And that gives a somewhat similar figure. And you could sort of confuse that and call it lurching, if you like, but it's not quite lurching. There are other effects you get, horizontal effects on bridges, centrifugal effects, obviously on curved track. Obviously, that's a fairly easy thing to calculate. Wind, of course, is a thing we need to think about. And a thing called nosing. Nosing, as the train gets along the track, it tends to shift from the flanges bear against one rail or the other, depending on discrepancies in the track and the rolling stock. And so you get this effect called nosing. And that wasn't introduced till 1946, came along very late, actually. One of the reasons for a lot of the early bridges being rather weak in plan is that they didn't really appreciate nosing. So it's been the downfall of some structures. But that force was, from very early times, was called 10 tons. It's a bit judgmental. I don't think 10 tons has ever been recorded. But it's now 100 kilonewtons in the Euro, so it's gone into Eurocodes. And it survived. No one's ever changed it. There are other effects we have to include. Train load surcharge behind abutments. Accidental train derailments is another thing we now have to think about. These early bridges, that was never designed for. If the wheels come off, you've got a major problem. But modern bridge floors, we have to have a continuous floor, either a steel or concrete continuous floor, which is designed for trains actually derailing. So that's something we have to do in modern bridges, which was never done in the early days. Now, there was another system around on the Great Western Railway. Instead of route availability, they had this other system where they painted little circles on the side of the engines to denote their route availability. So this engine was called a King class, had 2 red circles, and that meant it was banned from certain train routes because its axle load was nearly 23 tons, and we would call it RA8 now on the rest of the system. And these various other colours meant different routes, and they had a map, a route availability map, going back to 1920s, which showed these red lines, and some of them are double red, and you can see the Mid Wales lines are blue. These were where all the timber viaducts are that I mentioned, where the route availability was a lot less. So you had smaller locomotives with lower axle loads. So that system went on. I mean, it doesn't exist now. But I mentioned the heavy loads, of course, oil tanker wagons. We're now up to, these would be classed as RA10 because they've got a 25-ton axle, and 100-ton, it would actually be called in metric terms 102 tons. So we come to the modern loading. What is it? So instead of the previous loading I've shown from 1923, with the advent or the getting rid of steam, then a new European loading. This was developed in Europe, but a lot of involvement from the British as well in involving this loading. And this is the current loading that's now used today on modern bridge design. And you might say, it doesn't look much like a train, does it? Well, it doesn't. It was developed in that it's merely a system of loading which happens to give the same bending moments and shears as a lot of real trains. They just found that it gave the right answers. And it's quite a simple loading to apply, of course. So many of you will be familiar with this. It became in BS 5400. It was called RU loading at the time. So that's what's used today. And it actually represents, I say, a double-headed heavy freight train hauled by diesel locomotives. That's what it represents in terms of bending moments and shears on a range of spans. And the impactor factor is then, this is purely static. You imply this impact, phi, the impact factor, is this little thing here, which is just the formula, and I'll come to how that was formed in a moment. So that's the loading we use today. So what about the dynamic factors? We're just going back to the previous thing. I showed this phi. Where did that come from, that formula? It actually comes from a build-up called psi, 1 plus psi loading, which is made up of 2 components there on the bottom. 1 plus psi is actually 1 plus psi 1 plus psi 2. And those bits, psi 1 and psi 2, make up the phi I've shown on the previous slide. And you can see that it changes for high-speed track, because high-speed tracks maintain much better. You can reduce this second part. And those 2 parts, psi 1 is really the dynamic effects of the train on the bridge. In other words, the vibration of the span as the train goes across gives you a dynamic effect. In effect, as the train goes across, the bridge kicks back, if you like, and that impact effect is psi 1. And psi 2 is the effect of irregular track irregularities, if you like. The first one, Psi1, is based on a formula. And that's the formula, the basis of it, not the basis of it, but the formula is given, that little thing there, in terms of K, where K depends on the speed and the span and the natural frequency of the bridge, all the sort of criteria that you need. And it's based on a formula. And that formula, I've got the derivation of it at home, and Ian Bucknell, who is a renowned railway engineer, now retired, he actually wrote the derivation of that in front of me when I was sitting in front of him on 6 pages of A4 paper, which I treasure at home in his own handwriting. And it's the derivation, and there's quite a lot of clever mathematics in there, but he's written it in such a longhand way that even I can understand it. But Psi2, so that's the, if you like, the response of the bridge to the train running across it, the impact effect. And Psi2 is due to track irregularities, and that is in fact based on tests on bridges. And it's the formula for that is here. It's all in the Eurocodes. And it's also in the Network Rail Assessment document as well. And it's all based on European research, which had a lot of British input. So that's the sort of basis. But all this impact comes from this 1 plus Psi1 plus Psi2. And that led on to the, if I go back, go back to the previous one. What you do for designing new bridges is this phi, which is this very simple formula here, but that is based on Psi1 plus Psi2 for a range of different speeds and trains. It was actually based on a 13-year-long ORE investigation in Europe from different trains at different speeds. High-speed trains at 300 kph, 186 miles per hour, loco-haul passenger trains at 155 miles per hour, and heavy freight trains at 75. They bundled all that together and ended up with a curve, if you like. And that curve is that. If you draw that as a curve, that's what you get. So that's the sort of basis of it. It's quite important to know that, where that all came from. It's been written up in a paper you find in the Institution of Civil Engineers, 1974, a discussion at the Institution of Civil Engineers, chaired by Dr. Spindle, who was a famous railway engineer at the time, who developed or was involved in a lot of this development. So that's the basis of the dynamic factors which went into PS5 400 and then into the Eurocodes, and of course is current today. So I've just shown there the dynamic increments, and you can see here this Psi1 and Psi2. And it changes at 100 miles per hour, because when you get to a 100-mile-an-hour track, the track's maintained a lot better. So Psi2 is a reduced figure, so that's why you get this jump. Just the red hatched area is the steam train stuff. In other words, they were only going up to about 80 miles per hour. That's as far as they got. And the 1928 report I mentioned, the extensive testing of 52 bridges, this is what they came up with the impact a lot less. But then they were only going up to 80 miles per hour. But they didn't do much about the track irregularities. They did something about rail joint, but they didn't do much about track irregularities. In other words, the Psi2 bit. So that explains a lot of the difference. But now this is EUDL, equivalent uniformly distributed load, including dynamic effects. So that's everything thrown together. Span against EUDL. And you can see way back to the dawn of time, you're on our 1 ton a foot, and you should have been applying a bit of impact, as they said in 1849, up to 1.5 at short spans, and about 1.2 or so at 40-foot span, and then down to nothing for long spans. Whereas 1928, which is the RA system, including impact, that was called RB loading in BS 153. RB loading is in fact RA10, if you like, loading, 20 units of RA1 loading with impact for steam locomotives, and that's what you got there. And this was another formula due to some of the early formula there, which were a bit conservative. Whereas today, the UIC 71, the static loading is 71, but for modern bridge design, Network Rail current rules, you have to multiply by 1.21. Why do you do that? 1.1 of it is for possible future traffic growth, and another 10%, I call it 10% for luck if you like, but it's 10% to account for, I am told, for possible difficulty in future maintenance. In other words, degradation. So that's 1.21. So Network Rail now makes you design to this, which is a very big increase, in fact. In a way, it's sort of trying to be long-sighted, and they're looking to the future. But it does seem a bit conservative, actually. So that's where loading is now. You can see the enormous difference. I mean, take a 30-foot, about a 10-metre span. Then currently we're talking about 8.5 tonne a foot, compared with the 1 tonne a foot in the days of the very early days. So there's been an 8-fold increase in loading, total loading. And of course now we have high speeds, so the Eurostar here and the current version of it speeds up to now 320 kph, over 200 miles per hour. So what do we need to do about that? Well, one of the things we have to do is worry about additional vibration effects causing acceleration of the bridge. And I mentioned that on ballasted track that can cause instability of the track, which could be dangerous. You know, that they've had experience of France in that. So we have to sometimes on these high speed, this is more than 125 miles per hour, more than 200 kph, is do a dynamic analysis, and we very often will have to do that on high speed lines. Whereas if the speed's 200, in other words, 125 miles per hour, in general, we don't have to do a dynamic analysis. We can do all the normal things. We take the current loading, the LM71, and apply phi factor to it, and that's it. That's all we need to bother about. But if on a high-speed line, under certain conditions, I won't go into all this, but there are various conditions there. Does it comply with certain natural frequencies, etc.? You may have to do a dynamic analysis, and from that, you get the acceleration and decide whether your bridge is okay or not. And if it's not, you have to beef up the design. And this shows the range of bridges that it's reckoned you should try and stay within, is this hatched area here. But in fact, all these blobs I've drawn on here are a lot of existing bridges don't comply. A lot of existing bridges, some of these going back to 19th century, would just not be in this range. So that would mean that those bridges, if they were designed to modern standards, would have to have a dynamic analysis, and they'd probably fail. So they may well be capable of carrying RA10 loading or something like that, but they would not be suitable for very high speeds. So that's the general pattern. So we can't run trains at more than 125 on those bridges without doing a lot of work strengthening. And some of these bridges have, of course, been replaced. For example, on West Coast Main Line, some bridges have been replaced for that reason. And I've given there this deck acceleration criterion, 0.35 G on ballasted track, whereas in France they found at 0.7 G they were getting destabilized ballast. So they it's a sort of factor of safety of 2, I suppose, halved it to 0.35. And on direct fastened track, and that is slab track, in other words, no ballast, and that's what's being done on HS2, of course. They decided to go for slab track. So the criterion there is 0.5 G, which is of course half of 1 G. And at 1 G, of course, the wheels could lift off the rails. So that's the idea, to avoid that. Factor of safety on that of 2, we'll have it as 0.5. I don't know how arbitrary these figures are, but that's what they chose. And then for passenger comfort, you've got these reduced amounts of G. That's about 0.1 G for very good. That's to stop your cup of coffee spilling in your lap on high speeds, and then these different amounts acceptable on lower speeds of trains. And if you go for this dynamic analysis, if you have to do it, you have to use the Psi 1 and the Psi 2 up to these high speeds, and you compare the loading you get with the what I call the traditional loading, and also do an additional fatigue check. So you can see for high speeds, it's getting quite complicated necessarily. I'll just come to bridge failures now. We're over an hour now, so I'm running out of juice, I think. Bridge failures, these are important. This one collapsed in Southern Ireland about 15 years ago. And really it was longitudinal timber track, the old enemy. Pretty bad condition of track. The train came off and destroyed all these cross girders. No casualties, it was a freight train, fortunately, and no passengers. But bad news. I've listed here some of the bridges that have failed. I mean, there's comparatively few, actually, that have failed under traffic. You'll notice I haven't mentioned the Tay Bridge, the famous Tay Bridge of 1879. That failed with a train on it, but of course the loading that caused it was really wind. It wasn't really the weight of the train. It might have been a bit of wind on the train, but really it was a wind failure. And of course it was a badly designed bridge and bad workmanship as well. And it's a well-known failure. These failures here, out of this little list, 5 of them were cast iron girders. And all of those 5 had a casting floor, a blowhole, if you like, in the tension flange. And of course, modern technology we could detect by non-destructive testing whether you've got any faults in the cast iron. But of course, in the early years, you had no way of knowing when you had a flaw. I was involved in removing a bridge at Tring at the West Coast Main Line in the 60s. And over the side spans, which weren't over trains, there was an old cast iron girder. And when we took it out, it broke in half. And there was a casting floor in the bottom flange. Often wished I'd take a photograph of that, but I didn't. But anyway, you can see 5 bridges here failed through casting floors. And the last one in 1891, Norwood Junction, led to there were 5 people injured there, led to the total ban on cast iron beams. I mean, there are quite a few cast iron bridges surviving as arches, and of course cast iron columns, where you've just got compression stress. But tensile stress, of course, cast iron does not like. And then the latest failure that we've had was in 2009 at Stewarton, was due to corrosion, which I will come to. There were no casualties, fortunately. Just moving back to the Norwood Junction one, there you can see the cross-section of the cast iron beam. There was a blowhole there that led to the failure. And after that, the Board of Trade produced a report, get rid of cast iron, that's what it's saying. The necessity of strengthening on the company's railways in which cast iron girders are used. And that came national over the whole British rail system. People began to replace their cast iron with wrought iron or steel. And there was a lot of that going on. But as I mentioned earlier, it took to the 1960s to get completed. And that's just one I was involved in 1962 under West Coast Main Line, cast iron beams replaced by this unusual arrangement, rails in concrete, which was a very shallow method of construction. I often wonder about using second-hand rails in that configuration, but if any one of them does fail, at least you've got 9 more to take the load. But it's perhaps not something we'd get away with now, using second-hand rails. And this was the one I mentioned, 2009. Total, this was an absolute disaster. Under a freight train, doing 60 miles per hour, and 100-ton, 25-ton axles. So it was our friend the heavy axles again. But notice the classic horizontal shear failure there, and this was due to a line of corrosion all along the web, because the inside of that web could not be seen for inspection, and that was the cause. It was caused by corrosion. And there's the train across the bridge, 57 miles per hour. The locomotive got across the gap because the axle loads were only 21 tons, but the heavy wagons with 25 ton failed the bridge. Four heavy axles there. We got this classic failure. And the problem was all this ballast, which was covering up the sides of the girders, and there was various sort of timber cladding and stopping you ever inspecting. And the other fault was that an assessment had been done of the bridge, assuming that the webs of the girders were ½ inch thick. Well, they weren't. They were either 3/8, and for the edge girder, which failed the most, was only 1/4 inch. So there was a mistake in the calculations for the assessment. That's not the original design, the assessment, which was a pity. Bit of bad luck really to Network Rail, because they'd already decided to replace the bridge, and the new one was already made, but it hadn't gone in. So meanwhile, the failure happened. So that's been a real wake-up call, I think. And I mentioned this derailment. Our friend Longitudinal Timbers, very bad news. I was expert witness on this job. You can see how the timbers have rotted here and have been pushed sideways, and it's called gauge widening. And the train just dropped between the rails, if you like. And the problem was lack of maintenance, and the timber wasn't in fact one bulk of timber. It was 3 timbers side by side, which were only screwed together very crudely. So you had literally a pack of cards. I mean, when you got a sideways force due to nosing, that would just push this sideways. And there was hardly anything in the sides of the timber. There was remains of some old ash felt and a few timber wedges. The thing had been like that for months. There were 3 causes. The speed of the train was 60 miles per hour and it should have been 40. So it was overspeeding. The 100-ton bogie wagon should have been 100-ton, but it was actually, one of the wagons was loaded to 130 tons with spent ballast, overloaded, and the timbers were badly decayed. I always think accidents are caused by more than one cause, and you've got 3 causes here, all contributing. But the one which really was the main cause is the bad timbers. It was an accident waiting to happen. What about historic facts? We're nearly through now. Historic factors of safety. In the early days, they were assuming enormous factors of safety. On the other hand, we now have heavier loading. So did the high factor of safety compensate for the increase in loading? Well, the answer is, to an extent, it does. In cast iron, it doesn't. Cast iron, immediately, the safety factor dropped off rapidly because the loading was going up. And you got to a point here where you would get fatigue failure. Cast iron is hopeless in fatigue, and so that was totally unsafe. So cast iron, totally inadequate. In wrought iron or steel, if you assumed a bridge, this is all an assumption, and it just assumes a 30-foot span girders, and this is only an example, if you like, and it assumed a certain dead load, which I've just assumed something. And you can see how the factor of safety has dropped off. And it does mean, for example, in wrought iron, a wrought iron bridge built in 1875, that's, if there are any of them left, I'm not sure there'll be many, but if that had been designed up to the hilt for the design loading at the time, it now could only carry RA4 traffic. In other words, about 70% of RA route availability 10 loading. So it would be inadequate. It might still be carrying traffic, but that would be reduced loading. So you can see the high factor of safety hasn't compensated for the increase in loading, but it's helped. It has meant that a lot of these bridges have survived, but with the loading reduced. I'm going to finish on fatigue. I mentioned the bad performance of cast iron for fatigue. It's dreadful. Right down, this curve is right down here. This is a logarithmic scale of stress range, and what governs fatigue is stress range. That's the range of stress as a train crosses from plus to minus is the stress range against the number of cycles to failure. And you can see cast iron is pretty dreadful. But the good thing about cast iron is, though it's got a poor performance, if you use very low stresses, it's got infinite life. Whereas for steel and wrought iron, the way the code works, you get a steadily diminishing, so you will have a finite fatigue life, a much better fatigue life, but it does have an end to it. This is just based on the previous code BS5400. That's been replaced by Eurocodes, but it would be a very similar pattern. And I'm just going to finish with an example of fatigue. I've mentioned the standard box girders, originally called the Western Region box girders, and these on the Western Region originated, they were called the Lanthanum type from 1969 because the first one was at Lanthanum, which is near Newport in South Wales. That's the first one, went in 1969. And I think there were about 8 or 10 of that style, and then the design got modified later. But these, what we call the Lanthanum boxes, that's another picture of it there, and there's the construction. You can see with the box girders and then transverse ribs every 600 millimeters along there. That's the type of construction, and that is, of course, still a Network Rail standard design, not to Lanthanum details. And the Lanthanum detail is an unfortunate detail. You can see a detail. Here's the side of the box, a sloping side, and this is a ballast plate laid against to keep the ballast away. And the cross girder comes in here, and the floor plate stops just short of the end of the cross girder. So you've got a discontinuity there in cross section, an enormous discontinuity. And the thing is welded, of course. So any welding there, you will easily get a nick there, a welding discontinuity, and then probably an inbuilt residual stress, which will be in tension. So you probably had an inbuilt problem from the start. You can see what's happened. You can just see the fatigue crack, which has propagated down the web. And the bridges haven't failed, but you've got some of the cross girders have got this pattern of failure. Whereas on the right-hand side, I'm sorry, this has almost jumped out of the side of the screen, but I think you can just see that plan view that the floor plate is in fact shaped. You can see that scalloping there. So the floor plate actually does continue. It does continue to the end of the cross girder. So you haven't got the discontinuity. So the bridges that have been built in this 1975 modified design are okay. It's just these early 1969 ones that have failed. And what's happened? One of them, some 10 years ago now, has been repaired, and the repair done was to insert new cross girders between the existing ones, which aren't welded because it's impracticable to try and weld overhand there. These fabricated cross girders have gone in with an elastomeric or rubber strip to take out any unevenness of the floor plate. So it's a quite cleverly designed replacement. My opinion, it's a temporary measure. I can't see that lasting a long time. I can see this thing rattling about. I'd quite like to go up to that bridge and just see what goes on. It wouldn't surprise me if there were some movements and rattling going on, but I may be wrong. But I believe the other bridges of this type are being monitored by Network Rail, and I think at the moment they're deciding what to do about it. But to my mind, this repair, although it's very ingenious, and there was a paper on in the civils about it, I would regard it as a temporary repair. I think the future is on a lot of these old bridges could be fatigue problems. And I'm going to complete there. In conclusion, the American engineer Waddell, famous engineer, he said, famous statement, the life of a metal bridge that's scientifically designed, honestly and carefully built, not seriously overloaded, and if properly maintained, is indefinitely long. That's a very profound statement, actually. If you do all those things, your bridge could last forever. But if you don't do one of those, then it won't. Thanks very much.
Thank you very much, Alan, for a wonderful talk. I've forgotten how much I enjoyed the first time I heard the talk when you presented it to Cardiff in about, I don't know, 7 or 8 years ago, and especially your line drawings and watercolours. One of the comments from the audience, there's a few questions in, was not only is it interesting, but wondered whether you ever thought about writing a book. I think he suggests it might be a good read.
Yes, there is. It did get published by the Newcomen Society. I think it was called Train Loading on Bridges Since Stephenson's Rocket, I think. And then it also got published in the Bridge Engineer Civils, the Institution of Civil Engineers journal called Bridge Engineer, going back about 6 years, I think. So you can find that. So it's been written up to that extent, but it's not a book. It's a paper, if you like.
Now that's great. And then somebody else has commented that now they've seen the charts, all the various numeric information in the Network Rail standards now make sense. So that's quite good. So I wonder whether that sort of publication ought to be made a bit more readily available to users of some of their publications.
Yes. Sorry, yeah.
There is a question.
There is a question I made to 1974. It was an informal discussion, which is published in the Civils, 1974, hosted by Dr. Spindle, a famous rail engineer at the time. That's worth getting because that tells you where these impact factors came from. And you can look in various European research papers, but they're quite hard to get and to go through. But there's a summary given there by Spindle, and it's excellent.
Okay, great. We have a question in from Steve Matthews, who you know. He says, we now have a number of so-called metro or light rail systems, Newcastle, Manchester, Docklands, etc., which, although lighter in weight, do present different challenges in terms of the balance between static and fatigue loading for design. So I think that's quite a good question to follow where you finished off in terms of fatigue.
Yes, I've no experience of those, but yes, I can understand it. And of course, you're faced with very sharp curves as well. So centrifugal forces are quite something.
Yeah. I remember when I first joined Hayward, one of the projects I think underway was strengthening of Docklands Railway, because whilst the loading was quite light, they doubled the length of the trains.
Yes.
So all of a sudden there was a fatigue issue.
Yes, there was various strengthening done, and the bridges were composite, concrete slabs on top of steel beams, very like the one on the right-hand side there, the viaduct de Viquois, that system. And additional shear studs were put in because the original shear connection was obviously designed for the short length trains. And so additional shear connectors were put in from underneath by drilling up from underneath and putting in things, little spiral connectors, which are little Swiss rolls actually, which were squashed into these holes to form shear connectors, which seemed to work.
Yeah. And I think the other problem there was braking loading due to the extra long trains.
Yes, in fact, load sharing devices, that's right, yeah, were put in to share the longitudinal forces between more than a few spans. So the girders were continuous over several spans, but in bunches, I think, of about 4 spans. So to join them all together for longitudinal forces, these STUs, we call them, shock transmission units, were put in. And we've done those on a number of bridges. They're very useful to share loading between 2 abutments. Where you've got to think about expansion, you can still share the load between 2 abutments by using these STUs.
Yes, I've done that myself on a bridge in Wales. So the span is effectively floating, except for when it has to do with longitudinal forces. You've covered very well different materials, going from sort of cast iron masonry arches, wrought iron, steel. And a question from Simon Moon. He asks, do you believe that there is sufficient economy in using grade 460, a higher strength steel, especially in sort of half-through rail bridge construction?
Well, I think that there is, yes, particularly when you're tight for construction depth and construction width. Some of these bridges have got rather chunky with doubler flanges very often. So if you have a high grade steel, you might be able to get away with a single flange. So quite useful, I think. Not necessarily the whole bridge, but in certain, just maybe the main flanges.
Yeah, I guess other issues such as deflections or fatigue may govern some spans.
That's right. I've hardly mentioned deflections, but of course, Network Rail have requirements for that. I mean, the deflection the maximum you can ever have is span over 600, and it has to be tighter than that, depending on speed and span. So deflection does come into it. Yes, you would have to check that, but I can see that the higher grade steel, the 460, would have its uses, but not necessarily everywhere. Yeah. What we've got to be aware of is using very thin webs, I think, because they're vulnerable. I don't think I meant that shear failure I showed 2009 in Scotland. The webs were very thin, and shear is the worst failure you can get, because shear failures are sudden. Bending failures are normally, you can detect something's happening. Shear failures are instantaneous. So avoid thin webs.
Yeah, and I think my experience of a shear deficiency is that webs are often quite difficult to strengthen as well.
Yes.
Will Shout, Network Rail, comments that Stewarton possibly resulted in the requirements for hidden critical element examinations and sort of raised the profile of that much more.
Yes, it did. Yes.
Yeah.
That's very important for modern design. Allow space round your bearings and have jacking points for replacing bearings, and make sure you can see the ends of the girders. A lot of these old bridges, they were almost sort of bricked in with ballast walls and things, and you just couldn't get there.
Somebody else from Network Rail is offering you a job. He would like to bring resident engineers back, especially those who have design experience. Rare beasts these days. But another question from Network Rail, somebody called Steve Williams, and he wonders whether, having seen the UIC chart with the 1.21 factor, whether when we're considering times of lowering carbon footprint, should we really have a 1.21 factor?
Yes, it does seem a bit over the top to me. We don't know what's going to happen to loading in the future, of course, but I can't see it increasing a lot. In fact, with the getting rid of coal, we have no coal trains now and a lot less oil trains. We don't really have the heavy axle loads, perhaps, except for ballast trains, which are very slow moving.
And well within Network Rail's control, I should think.
Yes.
On the loading then, so one of two last questions now. Gareth Lloyd asks, again regarding loading, what your thoughts are using reduced live load factors when the live load is controlled, so sort of real train loading?
Yes, so in effect they do that for restricting routes to say RA4. I mean, on the Mid Wales lines, for example, RA4, RA5, whatever it is. I mean, that's controlled loading.
One last question. You've referred to the dynamic side of loading, speed related, and it would be ballast liquefaction, when the ballast sort of starts jumping about when the structure vibrates underneath. Has that been found to exist in the UK, for example, on HS1?
I've no knowledge of that. I gather they discovered it in France. As far as I know, it's not happened here. And they've got a good factor of safety against it. I mean, the 0.7G that they experienced in France, the limit here is half of that, 0.35 G. So they've played pretty safe with it.
Yeah.
And on
is one.
Sorry, HS2, I gather is going to be slab track, so we have no balance to worry about.
Yeah. Okay, that was the other half of the question. So well anticipated. Well, that's all the questions, Alan. Which thank you for those. Alan, that just leaves me. I don't believe I've forgotten anything else. I will have a little look to see if Kirsten or nope. That just leaves me to thank you very much again for a very informative talk. Wonderful slides, as I said earlier, especially your watercolours, and very clear explanation and answering of our questions. If we were all together in an auditorium, I would be asking everyone to join their hands together in the usual way. So you'll hear me and possibly Keith somewhere up in North Wales.
Okay. Thank you. Pleasure.
Thank you very much.